So thanks a lot. So to continue this conference, I want to tell you something about our recent line of work on the role of data structure in learning in shallow neural networks. So it's something we have been thinking about for quite a bit of a time now, but kind of made a real progress in, say, last year, together with these collaborators, so Florent Saclay and Marc Mézard, whom many of you, I think, know, and Federica, Sebastian, Bruno, who are postdocs in our group, and Galen Reeves, our colleague from Duke, thanks to whom we could kind of push the rigorous side of our work further than we would have been able without him. So this talk will be about supervised learning with deep neural networks. So just to set the notation to be on the same line, deep neural network represented as in this image with 4 layers given by the weight matrices W1, 2, 3, 4. The output of the neural network corresponds to this function f parameterized by the w's on an input data x, and the network outputs y's. So this kind of architectures, maybe not fully connected, but related ones, are core of machine learning as we know it today. It's part of reinforcement learning, unsupervised learning. So the way it typically works is that you're given a data set of labeled examples, a bunch of GPUs, and stochastic gradient descent is minimizing a loss function that is simply counting in some way the difference between the ground truth labels that somebody gave you and what the neural network is predicting right now. So, my occupation most of the time at work is to understand how this is actually working and what can be predicted about it. And when you try to build, say, a theory of deep learning, you realize that you kind of need to put together and consider kind of 3 basic facets of supervised deep learning. That is the architecture that is deep, and there seems to be something important about it. So we better keep that in mind. The algorithm, because you don't want to be just saying there exists a set of weights, you also need to be able to find that set of weights tractably. And the third side, which is the data, the structure in the data. And it's this third side that I want to focus on today that is kind of most often put aside when people think about theory of deep learning. So what's the status? Why the role of the data? What do we know? So we know from approximation theory that neural networks, such as the ones I showed you, can represent pretty any reasonable function. And these are works from 30 years ago. So that's the good news. So independently of what the data are, basically any function you want to represent can be represented by a neural network. But the bad news comes from computer science, and that is that if you actually were thinking about worst case data, then the computational problem of finding those weights is NP complete. So for worst case data, you're not able to solve the problem. So that's the bad news. But now when we look at the progress of machine learning in the last 20 years, on the empirical side, we see that on the benchmark data sets that we all have seen many times, learning is tractable. So kind of the big open question is, what is the property of the data that makes learning tractable? Because for worst case data, it would not be tractable. So that's the question that I will not be yet fully answering today, but that's kind of what the main motivation here. So on the side of statistical physics, because this conference is about interactions of machine learning and physics, what has been done for 40 years is to look at a very stylized kind of data set where the inputs X are IID Gaussian. So not only sample from sample, they are IID, but each of the samples has components that are IID. And the output would be typically created by a teacher neural network. And that's the kind of setting that Gardner and Derrida coined as the teacher-student perceptron. And we can solve this model, compute the generalization error with the replica method. And here I'm giving some key references, of course, missing many of them. There have been a lot of work on this type of problem. Now, clearly, the fact that here the data are, the input data are just random noise, it's kind of making us far from the realistic case. So, you know, even for such a simple case, this slide is just to kind of give you an idea how far away the kind of classical theory of learning is from predicting of what's actually happening in a typical case. So here I just use this teacher-student perceptron as like one case in which I can analyze things. And I can compute that as a function of the number of samples per dimension, the best achievable generalization error here is given by the black line. That's the base optimal error. No algorithm can do better than that from that number of samples. In orange, this is just out of the shell regularized logistic regression. So something very simple, you just take scikit-learn and you see that it is basically reaching the base optimal performance, the black line. Not quite, there is a little gap, but on this scale, the gap is basically invisible. And the green dashed line here, that's the generalization performance from kind of data agnostic learning theory. And you see that it's very far. And in the inset, you have the slopes. And as the number of samples is growing, even the slope is not right. So, you know, with this kind of theory, we are hardly hoping that one day, you know, the kind of aim here would be that one day we are able to take a data set such as, for instance, CIFAR 10, with, you know, its 50,000 samples currently, and say how many samples would be needed to really get a given performance. And this kind of theory that would be able to tell us that then could guide the choice of the algorithm and the architecture that we are actually using when learning, and we wouldn't have to rely, you know, on a lot of engineers to try a lot of architectures and algorithms. So again, that's still the aim. I will not be fully answering that today. But what I will be telling you about today is kind of our path forward to get to that goal sometime soon. And that path kind of builds on the strategy from the statistical physics of creating solvable models for data that are closer to realistic data. So these are the three references that I will be covering here. So when I say that are closer to realistic data, that kind of gives us an idea how we could go about creating such a model, and then we just need to like try hard and make it solvable. So how do neural networks these days create realistic data? Probably all of you have seen a picture like that or something similar, where these two people actually are not real people. These are photos generated by an generative adversarial network. That the way, you know, it's trained some way, you know, the classical way, but once it is trained, the way it works is that the generator in the GAN is a neural network into which you feed random noise and it outputs picture like that. So that looks very realistic. So can we kind of steal that idea of the generator of the GAN and create a model that will be solvable with, you know, the baggage of methods from statistical physics, but kind of, and you know, thanks to the fact that it will emulate the GAN, it will, you know, have the chance to be more realistic. So that's the idea, and kind of another aspect that underlies this idea is the observation that if you look at real data, they actually lie on a low dimensional manifold of the input space. It's not that they are filling the input space. That's kind of exemplified by the GAN, because the random noise that you feed in the input of the generator, the size of the generator is typically much smaller than the dimension of the input space. So that means that you can generate these images as a subset of the input space that is much lower dimensional. And this picture is kind of illustrating that. So using that idea, we define this hidden manifold model. The way that this model, so that's a model to generate synthetic data. The way it works is that I start with a matrix F that will not have to be random, that can be generic here, and that is kind of describing the coordinates of the submanifold, that here is just a two-dimensional sheet in a three-dimensional space. The input dimension here will be 3 on the picture. Then I take matrix of coordinates on that submanifold that I will call C in the talk, and that's corresponding to the blue points in the picture. Then I create the labels. So I take the coefficients on the manifold, the coordinates on the manifold C, and I use a teacher neural network to generate labels from these coordinates C. And then finally, the input data X, I create them by applying a nonlinear function sigma on the product F times C. So this kind of folds the manifold or hides it in the input space. And this will be my input data X. So kind of the key difference between the classical teacher-student model is not only the fact that the X here is not IID, it's a nonlinearity on a product of two matrices, so there are a lot of correlations a priori, but the labels are also not created by a teacher network from the data X, but from the coefficients of the latent space. So this kind of more corresponds to the intuition that, say, if you take MNIST images and you represent them in their lower dimensional in some lower dimensional representation, then in this lower dimensional representations, the labels are more visible, more easily visible. It's the lower dimensional representation that kind of shows up the function. So here I'm just summarizing it again. And this is just a definition. And the key property here is that at one hand, this model behaves similarly to what learning behaves on real data. And the next two slides will be about that. But crucially, we can solve it with the replica method and its variants in the same way that we can solve the normal teacher-student model. So to show you how it reproduces what we observe with real data, I'm really toy data. So here I'm taking the MNIST dataset and comparing how a neural network with just few hidden units learns to classify odd from even digits of the MNIST datasets. And the number of hidden units, that's the different colors of the curves. So 1, 2, 4, and 8. And I'm plotting the generalization error as a function of the epochs. And on the right-hand side is the MNIST, and on the left-hand side is data that were created by the random hidden manifold model of the latent dimension being 10. And the input dimension is the same of MNIST. And so you see that the curves look very analogous. And in both of them, you kind of exemplify the fact that as you are taking more and more hidden units, you're learning more complex function and getting the generalization error down. The second kind of numerical experiment to illustrate that this model has something interesting in it that the normal teacher-student model does not have is, now I do the same experiment as before, but I do it twice for two different random initializations. And I call these two trained networks the two students. And then I'm actually comparing the two students to each other. So if I compare them to each other on the test set, then they will agree quite often, as often as is the generalization error. So that would be the blue and orange curve here. The one would be, the blue would be the generalization error, and the orange is the agreement between the two students on the test set. But now if I don't compare them on the test set, but I compare them on just random Gaussian noise, then I see that they basically randomly disagree if I trained with at least 3 or 4 hidden units. And again, the MNIST behaves exactly the same way as the hidden manifold model behaves. This is kind of interesting because it tells you that even such a simpler neural network that only has 3 hidden units was somehow able to figure out that on the submanifold of MNIST, it should learn something, and out of it, it can learn just noise. So, and the model kind of captures that. So now about the solution, because all that would be kind of nice, but so what if we cannot solve the model analytically? Then we just are reproducing numerical experiments that we could have done on the real data to start with. So there is some prior work that kind of makes the solution possible. also ours, but I will focus here on this one where we solved the batch case, the generalized linear regression model. Ton Kulen was talking about generalized linear regression yesterday. So I will show you this case. So again, what's the setting here? So the data comes from the hidden manifold model. So that's the first line here, nothing changed. The teacher here does not have any hidden units for simplicity. And then the estimator that I will be analyzing is here just a rich regression with a loss that can be either square loss or logistic loss. That's the two that we will be typically looking at. It can be anything else, but it's just a generalized linear model, no hidden units yet. So what's different from, for instance, what Don was describing yesterday is that one, the data X here are not IID. They are not generated from a Gaussian. They have correlations in them because of this nonlinear function sigma. And the labels come from the latent subspace. They don't come from the generalized linear model. So that's actually not so evident how to solve this using the replica method, that we actually knew for 5-6 years, because mathematically this model is equivalent to learning with random features. And this is something that in the group I wanted to solve and have a solution for that since a while. And we just didn't know how to do that. And so I will not be going into details how this is related to the random features. Just to say that the key idea that kind of made the solution work, or observation or finding, is what we call the Gaussian equivalence property. And that's actually a finding that in the limit in which we are interested, that is that the number of samples and the dimension of the input space and the latent space all go to infinity with fixed ratios, that in this limit, the hidden manifold model, the learning on it, behaves exactly as if the data were actually generated as some constant times the product of the two matrices, as if the nonlinearity sigma was not there. Or in other words, as if actually the data actually came from a Gaussian covariance model. So the solution that Ton Kulen was showing us yesterday on the side of the input data is basically applicable here, thanks to the Gaussian equivalence theorem. Not quite, because the labels are still generated from the latent space, so this needs to be taken care of, but this turns out to be possible and there is no difficulty there. So we can write the replica solution of what is the generalization error if we learn a simple neural network on the data coming from this model. And this is how it looks like. And in the kind of red highlights, you see where the kind of key parts of the model come in. So the nonlinearity sigma that you put there to fold the manifold only comes through its simple coefficients, these kappa. And then the matrix F that, as I said, doesn't need to be random, comes in the equations through its Dirichlet transform, and that's all. And then the loss function and the nonlinearity that was generating the labels is coming in these special functions Z and eta. But otherwise, this looks like this looks familiar to the people who are familiar with how the replica equations usually look like. So that is something that we wrote in this paper. And having that, we can look at the phase diagram of this model, which has some typical features, as if we are looking, for instance, here at the least square. So this is for classification, where the labels are generated as a sign of the latent coefficients times some teacher. And the estimator we are evaluating here is the least square estimator for the classification. So there's least squares loss, and once we learn the weights, we are taking sign of the input to get the labels. And this is, we get curves depending on the regularization that are showing a peak when the number of samples is equal to the dimension. And kind of this heat map here is more interesting. It's kind of, okay, what does it mean? Here I am plotting on the x-axis is how many samples do I have per input dimension. And on the y-axis is the latent dimension per input dimension. And the fact that at the origin, the slope is kind of linear of this error, it means that even though the low dimensional structure was hidden by this nonlinearity, just a simple regression is able to take advantage or find back this low dimensional structure and get the error down as long as the latent dimension is comparable to the number of samples instead of the input dimension, as one could somehow think. So that's again kind of saying that even a very simple neural network is able to learn something about the structure of the data that is not completely straightforwardly there, say in the spectrum or something like that. So that's quite interesting. I will skip these 2 slides. And the remaining, say, 7 minutes or so of the talk, I want to spend on the question, this was a hidden manifold model that is inspired by the generative adversarial networks, but it is effectively only using one layer, generative neural network, right? The F would be the learned weights of that one layer, and then there is the nonlinearity and the input, and that's it. So a natural question is, can we actually generalize this analysis and this idea to deep generative models? Can we create the input data from several layers? And that's an interesting question. And the third paper that I was giving in one slide is answering positively this question. And that's what I want to show you here. So this brings us to the deep hidden manifold model, where the idea is similar. The only thing that is changing is that the generator now has more layers, and it doesn't even need to be a fully connected feed-forward network. So here, actually, the image is from a paper that I'm citing 2 slides later, that the generator is a convolutional neural network that is actually able to generate images that are quite realistic. So again, the data is generated by taking random inputs C to a generative neural network that I'm here just calling G. It can be something pretty generic that generates the data. And then the labels are generated as before using, so this time it's a committee machine. So one small hidden layer neural network with weights here that are the W tilde and V tilde. So that's the neural network that generates
test. Have I frozen or has Lenka frozen?
I think Lenka is frozen.
I think so.
Yep.
She's left. See if she can come back. Sometimes she might not notice that she's frozen because she's the one speaking. If we have a way to contact her outside the Zoom.
I don't know if you send a targeted message to one person, whether there's a.
She's not in the Zoom meeting anymore.
Oh.
But actually, that means that she would notice that, I think. So she probably is trying to come back.
Send her an email. Not sure whether she will read it. So I'm not sure what to do now, right?
Well, let's wait. I'll say, let's say, wait 1 more minute, and then we can just proceed to the next talk. Because there won't be, we can take questions on Lenka's talk later. She was very nearly finished. Let's give her 1 more minute.
Yeah.
Ah, she is back in the chat.
Seems to be back. I would think that in the office I have a more stable internet than at home, but that doesn't seem to be the case.
Okay.
Thank you, Sarah. Sorry for that. Now, Gabor, can you tell me where about you lost me?
Yes. So go there.
Here, this slide.
Just that.
This one.
Yeah,
Okay,
there.
great. So I start. So that's okay. So I start over this.
Actually,
this
the next one, I think.
Go to the next slide.
The next one.
Yes. Oh, sorry, that was too much.
Oh,
this one.
This we heard, yeah.
This we heard, yeah. Go
This you heard. Okay, great. And then here I was telling how what you actually do, how the solution looks like. Okay, so let's get back to it. Sorry for that. I hope it will stay stable. So the estimator that we are looking at here is the committee machine. So neural network with one hidden layer with just few hidden units, k of them. Now the key property again to be able to write a closed form solution for this model is again a variant of this Gaussian equivalence property, which here comes in the following form. You actually take lambda that are the pre-activations of the student and mu that are the pre-activations of the teacher, and you realize that they behave jointly as Gaussian. So they are not, you know, if you are at finite size and without taking this limit, they are not jointly Gaussian. But what the Gaussian equivalence property is telling you that they are sufficiently jointly Gaussian that if the learning assumes that they are, it actually is still asymptotically exactly describing the learning on the data that are not asymptotically jointly Gaussian. So that's kind of a non-intuitive and thing here that, you know, in the paper with Gale and Rees, we kind of put some mathematical ground on that, like central limit theorem for correlated variables. So that's the key that then, you know, once you have that, then it comes less of a surprise and you can do something, because if you can assume that these things are jointly Gaussian, then we can basically reproduce the kind of ODE analysis of the online gradient descent as done 30 years ago by Sad and Sola and related works. And the only property of the generative model that actually enters in these equations is the input-input covariance, this omega here, and the input latent variables correlations, this psi here. So the correlations between the inputs x and the latent space coefficients c. And is the spectral densities of these two matrices that enter the equations. And the equations look a bit non-intuitive and ugly, so I will not be showing you those. But instead, I show you basically an experiment with a very realistic generative model that here is, you know, taken from this paper 4 years ago in ICLR which is one of the state-of-the-art GANs for reproducing the CIFAR images. So on these little pictures here, that's actually the images that are generated by this GAN. These are not the CIFAR images. These are images generated by this GAN. And this here is a snapshot of the architecture of this GAN. So we feed random noise into this neural network, generate axes, and then we take teacher labels, and then we plot in the crosses here the performance that we see by actual training with stochastic gradient descent. And with lines, we plot the prediction of the ODEs that we derive that are only using these two covariance matrices that I was showing. And here there are two sets of experiments. So actually, if in this convolutional GAN we took random weights, so this would not be this would not be generating realistic images, but then the agreement between the theory and the experiment is completely perfect. We can even get a pretty good agreement if we actually use the trained weights, and the kind of little deviations that you see here, they are because of finite size effects, in a sense that the input to this generator is quite small. The dimension is just 100, and we need to estimate precisely enough the spectral density of the corresponding correlation matrices, and with just 100, the error in that estimation causes the deviations here. So kind of to confirm that this is really only a finite size effect, we took another fancy generative model, which here are the normalizing flows that are not even feed-forward neural networks. These are neural networks that are invertible. That's what's interesting about them. And for us, that makes it interesting that the input space dimension is actually equal to the output space dimension. So it's not so small, it's 3000 here. So this is something where, the spectral density is already quite self-averaging, so the theory should fit. And indeed, the fit between the learning that we get by actually running the experiment with crosses here just agrees perfectly with the solution of the ODEs we have. So this is giving us, for a first time, a analytic theory for the training on input data that are actually generating very correlated inputs. Here in the pictures, the top 4 lines are the actual CIFAR images, and the bottom 4 lines are the images generated by these normalizing flows. So they are not so perfect as this convolutional GAN, but they have a lot of structure in them. And with that, I go back to this slide with references, and this path forward of finding solvable models for data that are closer to realistic data seems to be pretty fruitful. And if you want to know more, please look at these references, and there are more of them to come soon. And with this, I want to thank you for the attention and open to the questions.
Thank you, Lenka. So the talk is open for questions, and there is one already in the chat. Is the manifold a linear manifold, i.e. a subspace in the construction? I think this refers back to your first model.
Yeah, so in both of them, so if I go back, so it's not a linear manifold, right? Because the function sigma that I put there, where is the, for instance, a definition that makes it nonlinear. Here, for instance. So the axis is a sigma on a product of 2 matrices. So if the sigma was just the identity or some linear function, then yes. But in the experiments, the sigma, we are typically using sine or erf. We are using a nonlinear function. That means that the manifold is not just a linear subspace.
Thank you. It became clear later in the talk. Thank you.
Oh, okay, sorry.
Next questions from Roberto Bondesan. Guys, do you want to just ask your question yourself?
Yes, thank you for your talk, Lenka. I wondered, so there is a recent interest in the community with respect to the neural tangent kernel analysis. And so I wonder, so if you can point out what are the benefits, or how do you see somehow your analysis with respect to that one? Because there we can also understand that the train dynamics for large with neural networks.
So the kind of line of work on the narrow tangent kernel, that's first of all, it's not concerning the structure of the data. It's concerning, the architecture. It's showing that, and kind of a little bit the algorithm, that in a certain limit of training, the deep architectures actually if the weights are not moving much, they are reducing to basically kernel retrogression. So, and that one is kind of more amenable to some understanding. But if you ask, experts on kernel methods, how are kernel methods influenced by the structure of the data? It's not that they know. I think we are more like learning that we don't understand so well kernel retrogression than other things. So yeah,
Okay.
to me, it's not very related. I mean,
Okay,
it would be interesting to kind of study the. You see here, I'm looking at estimator with one hidden layer, and I'm learning both layers. What I could also do, and that's that would be doable, I could be fixing the first layer and making the hidden layer large. And that is then converging, there's these random features that I was kind of skipping over, that is then converging to the kernel methods. And so I could be analyzing the kernel methods on the data coming from the hidden manifold model. So that would be interesting, to do, to kind of understand how actually kernel learning depends on the structure of the data, because it also does.
Sure.
And then NTK would be telling you, okay, and this is related to some limit to some probably not very interesting limit of deep learning, if it is not really learning features, but only doing kernel retrogression.
Can you go back? There's a request for you, go back to the reference slide. And while you do that, there's one last question, clarification. Can you, somebody?
Yeah, maybe I can ask. Hi, Lenka, thanks for this nice talk. I had a question. As I understand it, what you're doing is you're generalizing this online learning research to structured data, where it's no longer these random Gaussian input vectors. And looking at your learning curves at the end, you show steps divided by n. That means that you don't recycle data points. You assume that the data set is infinitely large.
Yes. So this second part on the deep generative models, that was the online learning, where I am not recycling data and the data set is infinitely large, as you're saying. The middle of the talk, the part was on the batch learning. So just gradient descent learning, or not really gradient descent. Yes, gradient descent if you want, but learning with the full batch.
Yeah.
And it's just that for the deep generative models, we did the online first. So the batch case would be in the more to come dot, one of them.
Okay, so thank you.